So in this video we'll be learning how to find the current, the thermal current that passes through a frustrum. So let one part of the frustrum that has the bigger circle have been in contact with a higher temperature body, and the one with the smaller circle be in contact with the colder body. So what we expect to see is that heat flows from the high temperature to the lower temperature. And in order to find out the current, the main challenge that we'll encounter is to find the relation between the radius and the distance x from the hotter body. So in order to create this, what we can observe is that notice how as x increases from 0 till L, let's just assume that the length of the frustrum is L. Frustrum is L. So what we have is that as x increases, here x decreases. So it decreases linearly. So what we can say is that the radius is a function of x, which is a linear function. It linearly decreases. So it can be expressed as ax plus b. So in order to find out what a and b are, we can just substitute two values and solve it. So first let's just substitute x as 0. So when x is 0, we have something like, so this entire term becomes 0. So we have b. But we also know that at x equals 0, it should be giving us an output of just R1. So we know b is equal to R1. And we know that at R is equal to L, which is the length of the frustrum, it should be given us a value of R2. So we can say that AX plus B, instead of B I can write R1, must give us R2. So we can just isolate A, and we have A is equal to R2 minus R1 by, so we have A is equal to R2 minus, oh my bad, I should be substituting L over here. Yes, AL. So we have A is equal to R2 minus R1 over L. We can write this, so substituting both of these values into the original linear equation, we have R, this is at a distance of x, is equal to R2 minus R1 divided by L times x plus R1. And the second task that we have to accomplish in order to solve this is to use calculus and find out how the current varies from each point as x increases. We know the general formula that let I be the thermal current. I'll just denote it by I. I is equal to K A dt upon dx. Here we consider dx to be in the direction of heat transfer. We know that heat always flows from higher temperature to lower temperature. So it's going like this. And as dx increases, it's evident that the temperature decreases because it goes from hot to cold. So instead of writing dt by dx, we'll be writing minus dt to indicate that it's a decreasing function. So, and this is, in this expression, K is the thermal conductivity of the material itself, and A is the cross-sectional area. In order to find out the value of A, A is basically pi r square because it's the area of a circle. And this can be further expanded. I can substitute this entire thing right now, but I think it would make it look a little ugly. So let me just write this as ax plus b, like how we had it before. But in the end, we can always just resubstitute the values and get the right answer. So can I just write it as pi into ax plus b the whole square, and that will be right. So I is equal to k pi ax plus b the whole square into minus dt upon dx. Having a 1 over dx term is a little weird, I guess, because it's usually seen in the numerator. So in order to do so, I'm just gonna bring dx term to the LHS. So what all the x terms together basically. So what you'll end up with is I dx divided by ax plus b the whole square. I've just brought the ax plus b and the dx terms to the LHS, and this gives me k pi into minus dt. And it's quite evident, right, that you have to integrate both sides. So that's what I'll be doing right now. What exactly are the integrating limits, you might wonder? So let's get to that. At x is equal to 0, we see that we're actually integrating it from all the way where x is 0 till all the way it's the length of the frustrum. So the integrating limits are just going to be 0 and L. And in case of the temperature, let me just take the minus outside. K pi integration. And when x is 0, you essentially just end up with the hot area, the hot body. And as x becomes L, you end up with the cold body. So the integrating limits are just going to be TH and TC. And in order to integrate 1 over ax plus b, what you would do is you would use the substitution method. And this is, oh, I guess I shouldn't have erased that. So let us just write it again. You'll have R2 minus R1 by R2 minus R1 upon L plus R1. Because when x is 0, you have just R1, and when x is L, you have these both cancels, you have R2. So that's right. So in order to integrate 1 over ax plus b, this is how you would go about doing it. So let's just assume this entire thing to be some r value. Let ax plus b equal r. So now, how would you differentiate r with respect to x? dr by dx is basically, how would you differentiate ax? Ax is basic differentiation of ax, just gives you a, and differentiation of a constant is 0. So differentiation of r with respect to x is just a. And this, so rearranging the terms, I get dx is equal to dr upon a. So I can substitute this into the original equation over here. So when I do that, this is what I'll be getting. So I can write this as I, and since I've substituted ax plus b into r, we have to change the integrating limits accordingly. At 0, when I substitute 0 into this, I get r1, and when I substitute L into this equation, I get R2. So accordingly, that will be my integrating limits. R1 till R2. And dx is basically dr over a. dr divided by a. And this, since I've already substituted ax plus b equal to r, this is r square. And this gives you minus k pi. And the integration of this is quite simple. It's just Tc minus Th. And we know that the integration of 1 over r square is basically minus 1 over r. So we also know that integration of, let's say, 1 over y square just gives you 1 minus 1 over y with like your y naught to y, similarly y naught to y. That's the formula, right? Same thing in this case. But I'll be skipping some steps. So what you'll end up with is I over L into minus 1 over R2 plus 1 over R1. And I can just multiply this negative sign inside because it'll simplify it quite a bit, which is k pi into Th minus Tc. So, I mean, this is a, my bad. So let me just clear some space. You can pause the video and analyze this if you want, because I'll be erasing this right now. Let's just write this part. I over a times, I can just write this term first and this term afterwards. So it's 1 over R1 minus 1 over R2 equals k pi times temperature hot minus temperature cold. It's important to not get confused with this A over here to area, because when I was finding out the relation between the radius and x, I clearly wrote this as ax plus b, and this a, the a that I've used here denotes this a over here and not area. And if you compare that equation and this, we can clearly see that a is r2 minus r1 over l. So I can substitute a as r2 minus r1 over l, which basically gives me r2 minus r1, and instead of dividing it by l, I can just multiply it by l over here. And I can take LCM from these two fractions, and that will give me r2 minus r1 upon r1 r2. So you can see that these both cancel each other out, and this just gives me k pi into Th minus Tc. And since the entire objective of this video is just to find out the thermal current, it's quite helpful to just isolate the I. So I can write I alone and take all the other points to the other side. So what I'll be what I'll be left with is k pi into Th minus Tc into R1 R2, and this everything divided by L. But I don't like to see the expression like this because it makes it kind of hard to see. Instead, what I'll have is k into pi r1 r2 into Th minus Tc upon L. We can verify this by checking some special cases. We know that the general formula is just I is equal to Ka dt upon dx, where A over here is area. And let's just consider a case where R1 equals R2. So that one, so when R1 equals R2, this one basically becomes R1 square, which is pi R1 square, which is basically the cross-sectional area, divided by dx over here length, which makes sense. That time you would have a structure that's something like, and you have a temperature difference out here. Similarly, when R2 equals R1, you're gonna have the same thing like that. And this is very similar to this formula because you have your K over here, and your pi R1 R2, which is kind of similar to like your area, which would end up becoming pi R square. And your dt, change in temperature, divided by dx, by your entire length. So again, this is the formula for finding out the thermal current that flows through a frustrum. Thank you.